Okay, so we're a couple minutes past, so we'll just go ahead and get started. So thanks everyone for joining us today for the PFAS Community of Practice webinar. For those that don't know or who aren't regularly attending the Community of Practice meetings, this is a webinar series that we're putting on for Sea Grant staff, sort of as professional development, but to align sort of with the themes that we're addressing in the community of practice as we move through the year. So the first theme for this year was sources and exposure routes. And so we had a webinar on Tuesday from Dr. Ellen Mallory from Maine Extension talking about agriculture as a pathway. And today we have Dr. Jahred Liddie from Harvard University here to talk about drinking water as our pathway. So Dr. Liddie is a postdoc at in the Harvard Biogeochemistry of Global Contaminants lab, working with Dr. Elsie Sunderland. He recently defended his PhD in population health sciences in the environmental health department at the Harvard T.H. Chan School of Public Health. Previously, he received his master's degree in environmental health from the Harvard T.H. Chan School of Public Health, and his undergraduate training was in environmental engineering. Dr. Liddie's research focuses on sociodemographic disparities in drinking water contamination by per and polyfluoroalkyl substances, or PFAS, temporal trends in PFAS drinking water contamination, and implications for population health due to widespread PFAS exposures. And Dr. Liddie is here today to talk with us about his research. So thank you, and I'll turn it over to you, Dr. Liddie.
Yep, thanks so much for the introduction, and thanks everyone for joining and for organizing this webinar. So today I'm going to talk about disparities in contamination by PFAS, or per and polyfluoroalkyl substances, in U.S. community water systems, focusing primarily on current understanding through my own research. And I'll also talk a little bit about data gaps and then efforts to redress these issues. So I want to begin just to give a really sort of broad overview of disparities in environmental health as a whole, bringing this down into two main components. So the first related to environmental exposure disparities, which have been identified for many different kinds of exposures, including drinking water contaminants. So that's really a question related to exposure. But we also have things related to environmental health disparities. And so these are theorized to occur both due to exposure disparities as well as to differential vulnerability. And so differential vulnerability can relate more to different demographic groups responding differently to the same environmental exposure in terms of health effects. So that's a really important point, although the focus of today's presentation is really on this question related to exposure disparities. And more specifically focused on drinking water and environmental injustice. I'm drawing on this 2014 paper that proposed what's called the Drinking Water Disparities Framework. And it really is aiming to propose a framework to explain how drinking water quality disparities come to be. And it breaks these apart into three main components. The first focused on the natural environment, second focused on the built environment, and then the third focused on the socio-political environment. And so really differences in these different factors across geographic scales and also between demographic groups are theorized to explain drinking water quality disparities. And so we see things like this related to climate and hydrogeology and soil, especially for geogenic contaminants or natural contaminants that you find in the environment. Things related to the built environment, and I think a lot of these are really important when we're talking about PFAS specifically. So things related to land use, agriculture, and infrastructure. But there's also the socio-political environment. So things related to planning and regulations, as well as enforcement of those regulations, historical settlement patterns that have shaped where people have moved around the US over time, as well as social vulnerability. And I also want to give a quick but kind of targeted overview of PFAS over time, with a specific focus on the US. So with really the high level point being that PFAS have gone from initial production in the US to ubiquity in the environment in just 88 years. So this timeline beginning in the 1940s with 3M first producing perfluorooctanoic acid, or PFOA, also known as PFOA, and the parent chemical to PFOS, which is perfluorooctane sulfonate, or PFAS. At the same time, DuPont also beginning to use PFOA to produce Teflon, so widely used in nonstick pans throughout this time period. This production by these two main companies continuing for several decades until DuPont is later sued for suspected contamination in West Virginia, and that being the focus of Dark Waters, if you've seen that movie. So that happened in 1998. And that later forming the basis of a class action lawsuit that continues for a few years after this. Later on, due to both public and federal pressure, 3M announces a phase out of production of PFOA and PFAS-related chemicals. That begins in 2000, and we see other companies doing similar things throughout this decade. That class action lawsuit beginning in around 1998 concludes, and then there's an independent science panel that begins to do research on both exposure and health effects of PFAS starting in 2004. At the same time, we actually also see PFAS present at high concentrations in polar bears, really indicating global transport throughout this time period as well. Later on, those science projects conclude in 2013. The EPA also begins to conduct a nationwide survey of unregulated chemicals that I'll talk a little bit more about later. That included several PFAS. So that starts in 2013 and ends a few years later. It really forms the bedrock of this landmark national study that I'll also talk a little bit about later, which later prompts this Senate-led initiative to study PFAS health risks. So we see at this point some national momentum in terms of the government on addressing PFAS. Fortunately, throughout this time period, we also see and continue to see replacement compounds in different environmental matrices. So GenX being a pretty well-known one, first reported in the Cape Fear River in 2017. And really due to a lot of those factors, as well as these replacement compounds, researchers propose, due to ubiquity in the environment, that PFAS have crossed a planetary boundary in 2022. Well, the upshot here being that in 2024, the EPA finalizes regulations nationwide for 6 PFAS in drinking water. And I'll touch a little bit more on that later as well. But despite all this, ultimately, why do we really care about PFAS? So we care about them because they're highly persistent, both in the environment as well as within the human body. And a lot of that is owed to this carbon-fluorine bond, which lends PFAS a lot of stability. It's also given PFAS this forever chemicals moniker, which you may have heard. There's also widespread exposures identified for PFAS. So things like drinking water, of course, that I'll talk about today, but also things in consumer products, really a wide variety of consumer products, as well as food, things like locally caught fish being a major focus in particular, PFAS being throughout the waste infrastructure, other matrices in the environment, including soil. And we also see, for infants specifically, transfer to infants through breast milk and cord blood. For drinking water in particular, there's a large population expected to be exposed in the US, above 1 nanogram per liter for PFOA and PFAS, about 200 million residents based on this study. And we also care about PFAS because there's really a multitude of adverse health outcomes that have been identified in association with PFAS exposures. These are broken down into higher and lower certainty based on a straight line or a dashed line in this figure. Some of the higher certainty health outcomes being things related to a few different cancers like kidney and testicular cancer, developmental outcomes like lower birth weight, and reduced response to vaccines among children, delayed mammary gland development, increased cholesterol levels, other cardiovascular health outcomes, and thyroid disease. So really, even just amongst these higher certainty health outcomes, you see a pretty wide variety of organ systems involved, different health outcomes involved. And so as you all likely already know, and why we're here today, is that PFAS are drinking water contaminants, among being all these other things. I mentioned earlier this 2013 nationwide survey that included PFAS that the EPA conducted, and that forming the basis of this study that's shown here in terms of this map. So you see in this figure, watershed regions around the country that had detectable and non-detectable PFAS based on that study. The study ultimately found a few different sources, including industrial sites, military fire training areas, airports that use film-forming foams that contain PFAS to fight fires, as well as wastewater treatment plants, all being associated with detection across this survey. Although really a major limitation of this initial survey, and where a lot of my research picks up, is that it had high reporting limits, which really limited the granularity with which you could look at PFAS concentrations around the country. It also included predominantly large community water systems, or CWS, that served over 10,000 people. And I'll touch a little bit more on both of these issues a bit later on as well. Although at the same time, and this again forming a lot of my own research, since 2015, several states have enacted drinking water monitoring on their own for PFAS, as well as have enacted regulations to address PFAS contamination in water systems. And so for my own research, a lot of this began by synthesizing this statewide sampling data set. And this being a data set of community water systems. So these are public water systems that serve the same population year round. This is kind of a subset of public water systems, which are different from private water systems that you may have heard of, which can serve single residences based on private wells. And so this, in general, is comprising this monitoring data from several states from 2016 to 2024. Throughout my own research projects, we've merged this with a wide variety of different data sources, things related to PFAS contamination sources, and I'm going to dig into more about throughout the presentation. Data from US EPA database on the Safe Drinking Water Information System that has all sorts of different water system characteristics, and also demographic composition. A lot of that coming from the US Census. And this data set has undergone many iterations throughout my own research. The latest version comprises 28 states around the country, about 11,000 community water systems included in total, serving close to a third of the country. Repository is actually available online, and I'm happy to share these data as well if there's interest, anyone attending today. And this is just a figure showing the breakdown by system size amongst these water systems included in this data set. So we see 80% of them are smaller, very small systems. Then we see smaller proportions of medium and large or very large systems. And this ends up being a major sort of advancement in some of the past data. This UCMR3 referring to this nationwide EPA data set that I mentioned earlier, starting in 2013. And then we see the statewide sampling data. Sorry, this is actually all active systems shown up here. The statewide sampling data is shown down here. So it more closely matches all active systems across the US when you break them down by system size, as opposed to this prior EPA monitoring data set. And as part of this research, I've also produced this interactive map that you can view online. The link is down there. Hopefully that still works. And then the QR code is also down there. But it shows a lot of these data in terms of these watershed units, which you can view some of the maximum concentrations identified in these units across these monitoring data. You can also view this broken down by county in terms of the systems serving those counties that have detected PFAS. You also see different demographic factors of those counties, both relating to racial ethnic composition and socioeconomic status. And then you also can see the locations of different PFAS sources. So those being military fire training areas shown there. You can see sites that have formerly produced PFAS, as well as some other sites as well. Just to give a brief data summary, sampling results for 5 PFAS are reported most consistently just based on state monitoring or state regulations. As I mentioned earlier, this comprises a larger proportion of small and medium systems compared to the prior monitoring survey, that also being more reflective of reality across the US as a whole. Ultimately, we found that about 1 in 4 residents served by these systems detected at least one of those 5 PFAS above 5 nanograms per liter. So before I jump into more of some of my own research, I want to talk a bit as well about kind of unite some of these topics on environmental justice and implications for PFAS, where you can see I think, pretty clearly that prior themes throughout the environmental justice movement have some implications for PFAS. So historically, the modern environmental justice movement was rooted in a lot of this place-based social movements among activists beginning in the South, with Dumping in Dixie and being a really key report on these issues by Robert Bullard. Later on, we have these reports conducted, Toxic Waste and Race in the US, finding kind of nationwide disparities in the locations of hazardous waste facilities nationally. And then the EPA also later conducting this report on environmental equity, finding similar issues nationally. With respect to drinking water in specific, as I mentioned a little bit earlier, you see disparities for other drinking water contaminants beyond PFAS. A lot of this summarized in this map, which is showing regulated contaminants at this point excluding PFAS, and their overlap in terms of drinking water violations with the proportions of people of color. So you see when these two things are happening simultaneously, you're getting evidence of environmental injustice within those regions. So now I want to talk about this first main project for today, which is titled Sociodemographic Factors Are Associated with the Abundance of PFAS Sources and Detection in U.S. Community Water Systems. So this was published close to 2 years ago on Environmental Science and Technology. I have a link at the end as well if you want to read it further. So this project had 3 main parts I'm going to give an overview of today. The first being trying to investigate this association between PFAS contamination sources and PFAS drinking water contamination, and that ultimately revisiting that prior study with those EPA nationwide data. Another question related to the association between demographic composition and PFAS contamination sources. So this focused more on siting related disparities in those sources. And the third, kind of combining these two, asking whether or not there is some relationship between demographic composition and then PFAS drinking water contamination. And you may ask, so why are we revisiting some of that earlier research documenting relationships with kind of a wide variety of PFAS sources? And so that ultimately boils down to the fact that there's a lot of presumptive contamination sites for PFAS nationally, which you can see in this figure from this 2022 paper. So around 57,000 sites, presumptive sites identified nationally. Some of these being military sites, major airports, wastewater treatment plants, industrial facilities that produce a wide variety of products. When you think about contributions to drinking water quality issues, it becomes kind of a question of who is to blame for PFAS in drinking water, and that being a really controversial issue over the years, with different sources blaming each other for drinking water quality issues, and ultimately being, in some cases, left to the communities to sort of figure it out. At the same time, over time, we have improved lab methods, while guidelines and regulations also lower, these ultimately leading to lower detection and reporting limits, so meaning that PFAS can be quantified at lower levels, and then that ultimately resulting in greater resolution in drinking water monitoring data. And so that's why we're revisiting this in this particular study. And this project, again, comprised 3 main parts. The first on this relationship between contamination sources and drinking water concentrations. So here we're looking at the locations of a few different sources, military fire training areas, airports, major facilities that previously produced PFAS, landfills and wastewater treatment plant effluent, and we're using these watershed units around the country to do so, these coming from the USGS. Second, we're analyzing this association between sociodemographic factors and PFAS contamination sources, focused on a few different racial, ethnic, compositional factors and socioeconomic status measures, and then focused again on those same 5 groups of sources. And then last, revisiting kind of the combination of the two on these demographic factors and detection of 5 different PFAS, as well as at least one of those PFAS above 5 milligrams per liter or above different state level regulations at the time. And next, I'm going to jump into some results. So the first results pertaining to this first research question. First, I'm going to give just a little bit of an overview of the 2016 study on those nationwide EPA data. And so that study finding really the single greatest association with major industrial facilities for PFOA, so an additional major industrial facility associated with an 81% higher PFOA concentration when it's located in the same watershed region as a water system. And then in purple is the same results from this more updated study, where we see pretty consistently for these two different groups of sources, high degree of similarity in the coefficient estimates between these two studies, that kind of being shown by how closely the orange and the purple bars are overlapping with one another. And this is despite a pretty large degree of difference in geographic coverage. So this is state level data versus subnational data versus nationwide data. The detection limits, which differ pretty significantly across these two data sets, as well as differences in the kinds of systems that are represented. And so here you see pretty similar coefficient estimate for major industrial facilities, and that actually being the single largest association across both studies. But despite this, it's important to note there's only 16 of these facilities nationwide. So these are facilities that previously produced PFAS. And although these are really large associations, really military fire training areas, for example, are much more numerous nationwide. So there's close to 330 of those facilities nationwide. So despite this being a lower coefficient estimate, these ultimately end up being pretty important predictors for drinking water quality. Now I'm going to move more into the second research question. This again focused on sources of PFAS and demographic factors, where ultimately we found that community water systems sharing watersheds with PFAS sources serve greater proportions of people of color. So you can see this in this figure summarized, where as one example for the percentage of Black and Hispanic residents, as that is increasing by 1%, you see a 10% increase in the odds of sharing a watershed with a military fire training area. Throughout this, we actually saw inverse associations with the percentage of the population below the federal poverty line, which went against some of our initial hypotheses. I'm not going to touch on that as much throughout the main presentation, but I'm happy to talk more about that later because we did investigate this further. And next, moving into the third question on drinking water concentrations of PFAS and sociodemographic factors, we found similarly to the second set of results I just showed that water systems with detectable PFAS serve higher proportions of people of color. And so this is shown in this figure for non-Hispanic, Black, and Hispanic and Latino residents. As you're moving towards the right of this figure, you're seeing that odds ratios above 1, meaning that detection is becoming more likely as these demographic groups are increasing. On the flip side, again, you see for the residents under the federal poverty line, the reverse is true, where as this group is increasing, the odds of detection is decreasing. We actually found that varied by urban and rural location, which I'm happy to talk about further. This was definitely an interesting finding. Just to zoom out a little bit, the levels analyzed here, 5 nanograms per liter for PFOA and PFAS, are just above the finalized regulations for PFOA and PFAS from the EPA, which are 4 nanograms per liter. This is shown in a little bit different way, which may be a little bit more intuitive. We're finding across the distribution of demographics that systems with detectable PFAS serve greater proportions of people of color. So you can see this in this figure. At the median proportion of residents who are people of color, you see pretty large difference between these proportions among systems with and without detections of PFAS, almost double the proportions. This generally holding throughout the distribution, even at the 90th percentile as well. Just to wrap up and conclude on this first project, so the statewide monitoring data that I've compiled are showing evidence of demographic disparities in PFAS exposures through drinking water. And based on some of our own analyses, these are appearing to occur in part, at least, due to siting-based disparities in the sources that we analyzed. And we found an agreement with the 2016 study, really here, despite differences in terms of the geographic coverage, in terms of detection limits, as well as in terms of the systems included in either study, that sources of PFAS, several sources of PFAS were again associated with drinking water concentrations. So the link to the paper is here on the right. And we also actually have all code from that paper, as well as all data from that paper available online. Now I'm going to pivot and talk about another project. This focused more on treatment technologies effective for PFAS removal, disparities in adoption of those treatment processes amongst US community water systems again. And so this is a paper that's under review, so just keep that in mind with a group of co-authors listed there. So we know from existing research that there's already evidence suggesting differences in household level costs of PFAS treatment, specifically when you're talking about water system sizes. So we know that from EPA's own cost estimates, as well as the study that's shown here that happened in Ohio, with the estimated median yearly costs per household for a group of systems in Ohio, and broke this down in this figure based on current yearly water costs, as well as additional costs annualized for these systems due to PFAS treatment. And so you see really the main takeaway here being that small and very small systems serving less than 500 customers currently pay the most based on the blue bars, and also would experience the greatest increase in costs if PFAS treatment were enacted in those systems. Nationally, zooming out, the EPA estimates annualized costs to be at $1.5 billion to regulate PFAS, the brunt of that being costs related to treatment. The American Water Works Association has a higher estimate, ranging from $2.5 to $3.2 billion per year. And more on the question of environmental disparities and environmental justice. Inadequate infrastructure, I mentioned a little bit earlier, kind of theorized to contribute to drinking water quality disparities. This figure is coming from a 2011 review paper, which kind of broke down water systems into these neat boxes and showing some of the relationships between these two different things. So we see the water system comprising the physical infrastructure, which is the focus of this particular paper, as well as the management and operational aspects related to finances and planning, and then also the day-to-day operations, management, repairs, improvements, monitoring, and reporting. And ultimately, these being important factors guiding the quality of the water at the top, as well as the cost and the reliability. The study ultimately found, based on this review, that most of the studies out there on drinking water quality disparities use finished water quality as their main focus. Although noting that such measures may not necessarily be as good measures of the underlying operational, physical, and regulatory aspects of water infrastructure. So this really frames the set of research questions for this particular paper. The first related to whether or not water system characteristics, specifically things like the water system size, are associated with early adoption of a set of treatment processes effective for PFAS removal. And then the second being whether or not sociodemographic composition of communities served by water systems are also associated with early adoption of these water treatment processes. So these questions are both really meant to understand which systems are vulnerable to not being able to enact these water treatment processes. And so the data, and I'll talk a bit more about the study design, but the data come from the US EPA, being a combination of publicly available data that you can find online, the Safe Water Drinking Information System, as well as data that we requested from EPA via a Freedom of Information Act request. And all in all, we have records for facilities managed by public water systems from 2004 to 2022. And here, really what we're studying is reported use of three different treatment processes, this being reverse osmosis, ion exchange, or activated carbon for at least one facility managed by a community water system. And we're focusing on these specifically because EPA considers them the best available technologies to address PFAS contamination in drinking water, and also consider them in its economic cost benefit analyses of the nationwide PFAS regulations. Just continuing a bit more on the data here. So we aggregate all those different treatment records, and then we merge them with a bunch of different other sources of data. Some related to water system characteristics on the left, things like the population size, as well as the source water type, the type of owner of that water system, the region that it's serving. So in the main analysis, we're looking at counties served, and I'll talk a little bit more about how we take apart that further, as well as total maximum contaminant level violations. So these are for regulated contaminants. We also integrate a bunch of different demographic data, variables related to racial ethnic composition, as well as sort of area level socioeconomic status. So these being measured by things like median household income, median household value, and then a bunch of other factors that we also consider. I'm not going to touch on specifics for these statistical analyses, but we're really following discrete time to event methods or survival methods. Really the main point here being that we're comparing how quickly groups of systems report treatment adoption over time. So that happening in the unadjusted analyses for a bunch of different factors and different groups of systems. And then in the adjusted analyses, we're focusing specifically on associations with sociodemographic composition while considering things like the year, the region around the country, the ownership type, the population size and density served by that system, the water source type, and maximum contaminant level violations as well. It's not as important, but just to kind of visualize what these data look like. This is actually a random set of data from this data set, where you can see events happening over time with those lines shown in red. And the system shown in blue didn't necessarily report treatment over this time period. And ultimately, we're having and adopting this staggered entry design. So really, we're analyzing this based on the years that have elapsed over time. So you'll see that in some of the figures coming up. And I mentioned digging into more specifics on sort of sociodemographic composition. So our main analysis is using county level demographic estimates based on data from the Safe Drinking Water Information System as well as the census. But more recently, the US EPA also made available service area boundary estimates and also known boundaries available around the country. So we also incorporate this sort of key sensitivity analysis, asking whether or not replacing all of these county level data with service area boundary level data affects what we see in our results. And so this is done using those EPA data that I mentioned. So this is known and estimated service area boundaries. So some of these are actually modeled by the EPA. Demographic data at the census tract level, as well as this nationwide population density data that's available at a really high resolution that enables us, so you see on the right, to estimate population in these intersecting regions, and then come up with an estimate for the full service area region, which is here shown in this black region, actually for the system that serves a lot of the Boston area. I'll get into the results in a second, but we conducted analyses for some main groups as well as a pretty large set of subgroups. So the main analyses are focused on systems with known PFAS detections based on several monitoring data sets, about 3,000 systems there, as well as a larger group of systems nationwide. Then we also stratify our analyses, so separate our analyses based on system size. That's based on the population served by those systems, by how urban that region is that system is located in, as well as I mentioned before, some other additional analyses. So some of those using service area boundary data. So now on some of the first set of results, this is from that unadjusted analysis that I mentioned earlier. But just to first describe this figure a bit further, so on the x-axis, we have the years elapsed, so 0 being the beginning of this study, so 2004 for most systems, and the end being 19 years later. And here we see very large systems serving over 100,000 people in this blue line. And on the y-axis, we show the cumulative likelihood of adoption of these treatment processes. So this is basically a measure of the proportion of systems at each time point that have reported adoption of these treatment processes. So we see this beginning at 0 based on our study design, and then this increasing for very large systems close to 35% at the end. And really our main finding in terms of water system size is that larger systems, so large and very large systems, are much more likely than medium, small, and very small systems to report adoption over this time period, with very large systems actually being 7 times greater than small and very small systems by the end of the study. We also see evidence of sociodemographic disparities in the unadjusted analyses. I'm focusing here on racial ethnic composition, but we found some similar results for socioeconomic status as well. So these are kind of similar figures, the years elapsed on the x-axis, the cumulative likelihood on the y-axis, and then here shown broken down by quartiles. So quartile 4 being a higher proportion, and quartile 1 being a lower proportion of Black, people of color, and white residents. So we see in general, systems serving greater percent Black and percent people of color were less likely to report adoption of the treatment processes throughout this study period. And we see the flip side observed for percent white. Although I want to note on the y-axis, and this is generally a pretty small range, really implying that reporting adoption of the treatment processes was relatively rare throughout this period of time. And then in the adjusted analyses of these, considering a slew of other factors, and us focusing here just on the demographic factors, we found most consistently for percent Black residents throughout these analyses that there were significant inverse associations with reported adoption of the treatment processes. In the main analysis, that's a 10 percentage point increase in Black residents is associated with a 19% decrease in the odds reporting adoption of these treatment processes. So we see that here for systems with known PFAS detections, as well as that larger group of systems shown on the right. And we see similar associations in general when we're stratifying and separating our analyses by these different groups. Specifically for system sizes, pretty similar results for proportion of Black residents. We see a reduced association, so this is going towards sort of the null or the no relationship among urban systems, although not the same for rural systems. And then we see in general a pretty similar result when we're using just surface area level data. Although nicely on this side, we do see, so these are all showing the confidence intervals. We do see a narrow confidence interval when we're using the surface area level data, just increase some of the precision in that model. And then this is summarizing a lot of those results in specific, combining some of the system size results with some of the demographic results that we found. So again, just reminding us, reported adoption of the processes was generally rare across systems overall. So about 5% of the systems do so by 2022. And this plot on the right is showing on the x-axis the percentage of Black residents going from 0 to 100%. And then on the y-axis, we're seeing the probability of treatment. This is actually the predicted probability for sort of like theoretical systems in this figure. So we're seeing this separated by large, very large systems, and then smaller systems of smaller population sizes. So we see for very large systems, when they're serving 0% Black, they have an 8% predicted probability, that decreasing to less than 2% at the far end of this figure. While on the flip side, we do see for small, very small, medium systems, they're sort of more consistently near 1% or less than 1%, ultimately showing us differences here seem to be more driven by system size as opposed to demographic factors like racial ethnic composition. So just summarizing some of these results, we found system size being pretty strongly associated with reported adoption of these treatment processes over this 19-year time period. We also found evidence of racial, ethnic, and socioeconomic disparities throughout the analyses. Sort of on some of the implications of these results in terms of policy, there's prior ongoing policy changes to support PFAS treatment in small and historically marginalized groups. And we see based on this analysis that those are sort of necessary to address these disparities. When specifically thinking about some of the high costs and economies of scale, as well as just some of the variation in systems in terms of technical and managerial capacity to support those actions to improve drinking water quality. And then our analysis wasn't necessarily a policy evaluation, although some of the study design, some of the methods that we use here can be employed in the future, I think, to assess responses to national PFAS regulations. So we sort of have that period before and then after those regulations have been put in place. So just bringing us back and then summarizing some of the conclusions overall. Based on that first project that I presented, we see evidence of disparities in the locations of PFAS sources and in PFAS drinking water contamination. And then in the second project I talked about, specifically in the adoption of treatment processes that can remedy that contamination. And then we also see additional evidence related to the contribution of sources to PFAS drinking water contamination based on that first analysis that I talked about. So I want to zoom out here and address maybe some of the elephant in the room that I'm sure all of you are pretty well aware of in terms of actions on environmental justice and other sort of environmental issues nationally happening currently. Here we see a pretty abrupt shift in priorities federally on this. In terms of infrastructural money, some of that being relevant for combating PFAS contamination in drinking water.
Jahred,
And some,
I'm sorry to interrupt, but we lost the visual of your slide.
Oh, sorry. I'll try and reshare. I think something did happen there. I'm going to stop and then try and reshare.
Sure.
Sorry about that.
That's okay. Got it. Okay. We're in the presenter mode. We can see presenter mode right now.
Oh, sorry. I will try again. Hopefully you're seeing the main set of slides and not presenter view.
Nope, not presenter view.
Okay, awesome.
Yeah, now it's working.
So yeah, just to recap on this, addressing some of the elephant in the room on these issues. So we've seen pretty abrupt shifts in priorities related to environmental justice, as well as a slew of other environmental issues. Some of them is also related to infrastructure money, some of that meant to address PFAS contamination. This older environmental justice executive order being scrapped, as well as tools that EPA has previously produced also being removed from online, although I'll note that specific tool has actually been archived. I'm happy to share that archived version as well. Although I don't want to end on that negative note, I want to try and end on a more positive note, and I want to highlight two things on this. The first set of these being more related to advocacy and action on both issues related to PFAS as well as issues related to environmental justice as a whole. And these both really have a history of occurring at local and state levels. So I'm linking two articles here. I'm happy to share in the chat as well. The first on top is an interview with the former head of the Environmental Justice Office at EPA. She digs into some of these issues, as well as efforts ongoing at state and local levels to address these issues. And then a more recent opinion piece in the New York Times by Mariah Blake on PFAS advocacy over time, and then affected communities around the country and what they've sort of done in their own local contexts. And then the next point on this, I didn't talk about this in depth today, but this is another ongoing project under review with myself and then a few other colleagues, where we propose some actions really to increase the transparency of drinking water quality data, so that affecting PFAS as well as all sorts of other drinking water quality contaminants. We find in this paper, we do this sort of short literature review where we find really there's been a lot of focus regionally or at the state level as well on these issues. So there's a history both in terms of advocacy and action as well as on research addressing this sort of beyond or below the nationwide scale. So I want to end here and acknowledge the Biogeochemistry of Global Contaminants Lab here at Harvard, led by Elsie Sunderland, as well as other collaborators on the work presented, Dr. Lowell Shader, Mona Dai, Professor Cindy Hu, my dissertation advisory committee who helped me on some of this work, and then state agencies and the US EPA for providing data and letting me bother them over many years on these projects. So thank you all as well. I'm happy to take questions now from the audience.
Thank you so much for that talk. It was fascinating to receive this wealth of knowledge. So thank you for sharing that with us. You've collected some very, very valuable data, I can see, and you were also asking some very interesting questions. So thanks again on behalf of everybody. Folks online, if you have any questions, please feel free to use the Q&A feature to share any questions, and I'll read them out. And I have a few questions here already lined up. There are a couple questions regarding the first project that you talked about. The first one is if you could expand a little on the disparities between communities under the poverty line versus communities of color, because you would expect a similar trend. And the other question is also related to this, so maybe you want to address this when you're talking, is the difference between urban and rural areas, particularly with poor populations, but again, relating to the first paper.
A great question. So I didn't talk about it in depth in the main presentation, but we noticed in aggregating a lot of these data, and specific for the sources of PFAS that we were analyzing, that many of them are more clustered in urban regions around the country, in more densely populated regions as opposed to many of the rural regions, at least for the sources that we're analyzing specifically. We also see across these states, in general, the urban areas at the county level, you have lower poverty rates than amongst many of the rural areas. So some of that actually being reflected of some of the concentration of poverty in rural areas in the US. I think ultimately that is why we're seeing in this first analysis across all systems, so this including systems in rural and urban regions, that this is negatively associated with contamination, which would not necessarily go in the direction that you would expect. But because of that difference in the source profile that we saw, we ended up splitting this out based on population density, so focusing on systems in more dense regions around the US and then systems in less dense regions. And we found a similar, although reduced association amongst urban systems specifically, although we see amongst rural systems, you actually see the flip side is shown where being below the poverty line, having a greater proportion of residents below the poverty line is positively associated with contamination. So that is maybe more in line with what you would expect. And I haven't necessarily investigated this further. I think there's also a bunch of other potential sources of PFAS that are more specific to some of these rural regions that also could be explaining some of those results.
Thank you. I do
I have
have one other question. Oh,
I have a
sorry, go on,
follow-up.
Sarah.
Yeah, sorry, I have a follow-up for this. So
Mhm.
do you think that this is because more urban water systems tend to be larger? And the difference in socioeconomic disparities is kind of overshadowed by the impacts that a large water system is having versus a smaller water system?
Yeah, that could be part of the reason. We do in some of the final models that we have, we do also adjust for population size based on water system size. So it is not solely explained by that, although it's possible to partially explain by that. It is interesting as well because you would, for sure, there are more large systems located in urban regions around the US, but you actually do have a pretty large group of small systems also located in urban regions in the US. So it's a little complicated to just think of urban being large systems and small being rural areas. It's kind of a combination of the two.
I have a
Yeah,
Chicago
not fully
bias.
explained.
Um, I'll go on to the next question, which is what accounts for the disparity in estimated treatment costs between the EPA and the American Water Works Association, especially considering the fact that the American Water Works Association is part of the lawsuit hoping to strike down the drinking water rule? That's a
Yeah,
great question,
that's a
Sarah.
great question. I may not have all the answers on that. At least I know based on reviewing some of the analyses that they put out. So they had a consultant do this analysis. I think it's Black and Veatch. It is a bit difficult to find a lot of details on how they arrived at that estimate. I think they say that they consider more system-specific factors in terms of what would be the kind of optimum treatment process for that system to put in place based on more detailed information than they say that the EPA had available. Although, yes, it's important to note they're also uh, engaged in an active lawsuit against the maximum contaminant levels.
It's very interesting. And the next question I have here for you is, are all the community water testing or community water systems testing for PFAS now? If it's not yet required, one would imagine that many of these systems, especially the smaller ones, aren't yet doing rigorous testing for PFAS. And if they don't have the money or a requirement to remediate, there's no incentive to really find this out. Is that something you think is supported by your data?
Yeah, that's a good question. We at least see throughout the state data that's been compiled so far that there are a large number of smaller systems that have done testing. So some of that in these surveys has been supported by the states financially. So that has been probably a reason why some of those systems are able to do monitoring and do monitoring pretty early on as well. There is now, I mean, under the Biden administration, there was an expectation that systems would complete monitoring by 2027 nationally. I didn't touch on this specifically today as well, but there is also, so I mentioned this, 2013 study that, or monitoring survey that the EPA did. There's now a current one happening now. It's supposed to end in 2026. And so that specific survey, there is a call for more medium, small, and very small systems to participate. So some of that should be supported federally. I don't necessarily know what the priorities are. I'm currently on that. I think it's a little unclear whether or not those priorities will continue to be the same, especially for small systems.
Yeah, and related to that is a follow-up question. If the availability of funding for remediation in the community water systems is correlated to the size, you think, or maybe it is if it is really a priority for the water system or not, if you've seen that in your work so far.
Yeah, it is always been a goal of mine to be able to find nationwide cost data in terms of not necessarily even cost of water, but the cost of funding put in for infrastructure management and operations of systems nationally. It's not really available at that scale. My guess, at least based on some of the EPA's cost benefit work, and then based on other studies I've read, you would expect for sure that there would be less funds available among small and very small systems. Some of that also just owing to the fact that they have a smaller population base that they're giving water to, so there's less revenue. And then I also think of economies of scale. They have to kind of pay more on a per volume basis to do the same thing that a very large system would be doing. But I don't necessarily have that data available at this scale. That's a great question.
Well, I know as part of the drinking water rule, wasn't there a grant program that was supposed to be instituted too that I imagine that is on hold now? Although maybe not if the drinking water rule is still that, like it's still okay until the lawsuit happens. Maybe communities can scramble and apply for some of that money quickly
Yeah,
before
and
they pull it out from
yeah,
under.
yeah, and there are also drinking water state revolving funds that at least I've heard are still underway, where the EPA kind of lets states have access to funds, and then they can sort of provision those out based on applications from systems. It still is kind of based on like a system going out and saying that we need this money to do this infrastructural update. So there is still some onus on systems to be able to do that. But at least I've heard that it's currently still happening. I'm not sure specifically for the PFAS MCLs if those are all going to happen or not.
Yeah.
Related to, the current climate that you were mentioning towards the end of your talk, do you have a sense or a feel for how the funding landscape for work like yours might change, or at least for the next few years?
Yeah, unfortunately, I don't, especially as an earlier career researcher, we've kind of been, I've sort of now was going into some of the more experience on trying to think about grant writing and work with others on grant writing. There's been a lot of, I think, delays in that, just with a lot of changes happening at NIH currently, NSF as well. I don't necessarily have a good answer. I think some of that will ultimately be taken up by private funders and then other funding sources. Although I think it is still a little difficult to fully make up the gap that those federal funding sources had previously. So I would still expect for sure people will be doing work related to this over the next few years, although I think there are necessarily going to be some funding constraints on that from the federal government at least.